Welcome to lecture 6. So this one is the last one, so I hope you are enjoying my course. And as I told you today, actually I have like two main results to tell you. Actually the first one is a result, the second one is not a result, it's an open problem. So today I'm going to make me a little bit of pleasure, so I'm going to enjoy this lecture and I'm going to tell you about some open problems. So, well, first I'm going to tell you about a theorem, so something that is really proved, but that it was very hard, and it was kind of the inspiration for so many other open problems later. So, enjoy it. So, the title for today, for this lecture 6, is Falkens Theorem and some height conjectures. So first I will talk about Falkens Theorem. So maybe you have heard about Falkens Theorem. So I'll say it later. And then I'm going to say something about some open problems related with Diophantine geometry and all the height machinery that we have developed during those lectures. So, okay, first about Falkens Theorem. So, this I guess that you know. So, for genus 0, this concerns the number of rational points on curves, right? So, imagine first that you have a curve of genus 0. So, actually here, for the number of rational points, we have two possibilities. The first one is that we have that our curve is isomorphic over the rationals to P1. And then, in this case, the number of rational points of the curve is equal to infinity. I have infinitely many rational points, okay? And they are all parameterized by P1. So this is good. Or the second situation is that actually the curve is not isomorphic to P1 over the rationals. And then, in this case, we have that the number of rational points is equal to 0. So basically, we are in the two extremes. Or we don't have any rational point, or if we have at least one, then we have infinitely many. Okay, what about the genus 1 case? Well, the genus 1 case, it may happen that we don't have any point, right? So we are still in this case, 0 points. And then if we have more than 1 point, then C is what is called an elliptic curve, right? And we have been studied, like in previous lecture, in lecture 5, the set of rational points of an elliptic curve. So, we know that in general, the rational points of an elliptic curve, this is equal to the torsion points, right? Plus set to R, where R is the rank, and we have all these open problems and interesting problems also concerning the rank, right? That I'm not going to repeat. But here actually we have many possibilities, right? Because we can have like a finite number or an infinite number if the rank is greater than 0. And for the finite number, actually we had this measure theorem, so it really tells you like the possibilities that you have for this finite group. So, we know what is happening here. And now the question is, what happens for genus 2? Or for genus even greater or equal than 2? So this is Falkens Theorem, who is going to tell us the answer. Okay, so Falkens Theorem. Falkens. Let K be a number field and let C over K be a curve of genus greater or equal than 2. Then, and this is the result, the number of points of the curve, over K, the number field, is finite. So, for genus greater or equal than 2, we cannot have an infinite number of points. Not only over the rationals, but over any number field that we fix. It is finite. So, I mean, of course, then the natural question that you can ask later is, can we compute them? Is there an algorithm to compute all of them? And actually, no, we don't have an algorithm to compute all of them. So, I mean, this uses the theory of height. And I mean, I was repeating all the time during the lectures that actually, in general, all the constants that appear when we play with the height, they are explicit ones. And we can compute everything explicitly, but not here. And you will see why. So, there is a finite number of points, but we don't have a constant, like a explicit constant, and we don't know how to compute them. And I mean, actually, this is like a field of research, like there are many people working on this, right? Maybe you heard recently about this fancy new method, Chobot. So this is a method that is very useful for computing points on curves. And there are a lot of good people working on it now. So, I mean, there are, again, a lot of nice problem questions related to this thing. But unfortunately, we don't know how to compute it. So, I mean, actually the first proof by Falting of this result, and somehow this is why, I mean, this bound is not explicit and there is no algorithm to compute them. The point is that the proof was very complicated. So it was using like very, very high strategies and deep mathematics, and it was very difficult to follow. But then that was in the year, let me look at the year. So, I mean, actually the result was Conjecture by Mordell. So, you know Mordell is one of the theorem from the previous lecture. So, Mordell Conjecture this result in the 22, almost 100 years ago, and Falting proved it in the 83. So, I mean, it took quite a few to prove this theorem, so it was really complicated. But then Botja got an easier proof of Falkens Theorem. Because, I mean, he got like a strategy, an intermediate lemma that allowed to prove Falkens in an easier way. And then Falkens even got an easier proof. So, I mean, let's say that after this proof, Botja and Falkens, they were working on it, and they kind of simplified the proof. So even in this way, the proof is complicated, so I cannot really do the proof like in 1 hour. But what I'm going to do is like to state a Botja result, inequality, and from this result, we are going to prove Falkens theorem. Okay, so let's see this result. So theorem, Botja inequality. Let's see over K be a smooth projective curve of genus greater or equal than 2. With the set of rational points not empty. Right? So, I mean, if we want to prove that it's finite, if it is empty, we are done. So, let's assume that it is not empty. Okay. So, in this situation, they are constants, K1 or kappa 1, that actually depends on the curve, and kappa 2, that is independent on the curve, but that it depends on the genus of the curve. Such that if I take two points, maybe not different, on the curve, but not rational, so I'm taking here the algebraic closure, so 2 points on the curve, such that they satisfy the following equalities. So the norm of Z is greater or equal than kappa 1. I'm going to recall now who is the norm. Okay, of course I'm using the height. And the norm of W is greater or equal than kappa 2 times the norm of Z. Then the pairing associated to these 2 points is smaller or equal than 3 divided by 4 of the product of the norms. So, I mean, this is what is called Botja inequality. So, I mean, just to recall, so here we have height. So, basically, what is the idea? So, we consider the Jacobian of the curve. So, this is an abelian variety. Theta is the theta divisor. So this is the divisor associated to the curve being inside the Jacobian. So we have an abelian variety, we have a divisor, so we have the canonical height, the Néron-Tate canonical height. Néron-Tate. Canonical height that we denote like this. Right? So with this we can define a norm for a point such that it is the square root of the height. So we have this norm. And now with this norm we can define a pairing in this way. I mean, it's the same thing that we saw, well, in previous lecture. So, I mean, it is a little bit hidden in Botja inequality statement, but basically here we are stating an inequality with the heights of the points. Okay? So this we are not going to prove it, but we are going to use this Botja inequality to prove Falkens theorem. So let's go. So proof of, well, how Botja inequality implies Falkens theorem. So the idea is as follows. So we are going to consider the kernel of this map. The Jacobian, or the k rational points on the Jacobian, okay, we can see them into this. So what is this? Those are the k-rational points of the Jacobian, but I'm doing the product, the tensor product with the reals. So basically, who is the kernel of this map? The torsion points. Because if a point, for instance, 3 times the point is equal to 0, then this point goes to p times 1, right? But because this is the reals, this is the same thing that 3 times p tensor 1/3. But if the order of p is equal to 3, then this is going to be 0, so this is 0. So the kernel of this map, so I erase it because I'm going to keep writing, but is the torsion points. Okay. So the kernel of that map, of this, is the torsion group of the Jacobian, which we already know is finite. So now, in order to prove that this is what we want to prove, right? That the number of rational points of the curve is finite, we will prove that its image in here is finite. Right? Because we can see the rational points on the curve into the rational points on the Jacobian. And I mean, actually, to define this embedding, we need to have a rational point. So, I mean, this is why, but we have that condition, right? I mean, if here we don't have any rational points, then we are done, because this is a finite number of points. If I at least have a point, then I can use that point to construct this embedding into the rational points of the curve, into the rational points on the Jacobian. And then I can look at the image in here, where I do this tensor product, and I mean, it's enough, because of the kernel of this map is finite, to prove that the image is finite, to check that this was already finite. So this is a strategy. We want to check that the image of the points, of the rational points of the curve into this tensor product is finite. This is a strategy. Okay, so let's see how we do this. So let's go back to the bilinear form we just defined. So the bilinear form that we defined just before makes this space, the tensor product, into a finite dimensional Euclidean space. Right? Why do we know that this is a finite dimensional Euclidean vector space? Because it is finitely generated, right? I mean, this is a Mordell-Weil theorem. This we know it. Okay, so we have this Euclidean space, and we are going to define the angle between 2 points in this Euclidean space. So we define this angle as the real number, so this is something in this interval, 0 pi, such that the cosinus of the angle is equal to this. So this is the standard thing, right, that we do in Euclidean spaces. So we have this definition for the angle. And with this definition of the angle, we can define the following cone. So, I mean, this is really what you are thinking. So, I'm going to get a point, and I want to consider all the other points that they are like inside an angle. So, I take my point, I take like an angle because I define what it is, and I want all the points that they are inside that. So, this is intuition. Let me write it down. So, gamma of x0, x0, and theta 0 equal to the points on this Euclidean space such that the angle between the 2 points is smaller than theta 0. Okay? So this is really what you have in mind. So for instance, I mean, as an example, imagine that this is the point x0, right? So I take here another point x, so the angle is this one, right? So if I want all the points with an angle smaller or equal than theta 0, you may imagine that I have, maybe I can take another color. So imagine that this is theta 0, so I take it also on the other direction, theta 0. So basically, because I fixed this point x0, so this cone is just this. And I mean, this is like really like an angle because I did it in 2 dimensions. But I mean, you can think like in 3 dimensions, you have like a cone. Okay, so everything that is in this angle. Okay, it's good to have intuition, you will see why. Okay, so we have defined this angle and the cone. So let's see how we can use Botja inequality with this. Okay, assume that the cardinality of such a cone with the rational point on K is equal to infinity. Okay? Actually, well, I can't tell you what is the idea. The idea is that we are going to cover all the Euclidean space with those cones. Okay? So we want to prove that actually this is not possible if the angle has some properties. So the idea is that we're going to prove that there are only a finite number of points in that angle, in that cone, and then that we can cover all the space with a finite number of cones. So if I have a finite number of cones, each of them has a finite number of points, the total number of points have to be finite. So, I mean, this is the idea. So let's see that this is not possible under certain condition on the angle by using Botja inequality. Okay, so assume that it is infinite. Then there is set in that intersection such that the norm of set is greater or equal than kappa 1, the first constant in Botja inequality. Why is this true? Because we know that the number of points with bounded height is bounded. So if I have infinitely many points, it means that I can find points with the height as big as I want. In particular, bigger than this kappa 1 that we have in Botja inequality. And then we can find W in the same set, because it's an infinite one, such that the norm is greater or equal than kappa 2 times the norm of set, right? This is because we have infinitely many. But now we can use Botja inequality. So then we have that the pairing of these 2 points is less or equal than this. But then what does it mean? Recall that this divided by this and this is the cosinus of the angle associated to the 2 points. So basically this implies that the angle between the 2 points is greater or equal than P divided by 6, right? This we get it from Botja inequality. But wait, so what is the conclusion? Let's go back. The idea is that here we just assume this is infinite, okay? So under this circumstance, this implies that the angle has to be bigger than this. Okay, but now we can say, let's take an angle that is smaller than this. Then I cannot have infinitely many points. So then, in particular, this means that this, I'm going to take something smaller, so pi, for instance, divided by 12. Instead of by 6, by 12. So this is smaller. Then this is finite. For all x0. So the x0 is irrelevant. But now is the thing that we said, that actually Jk, the Euclidean space we started with, is covered by a finite number of cones. So, we can find xi such that this is equal to the union of gamma xi pi divided by 12. And this is a finite one. So I from 1 to r. So then this implies that the intersection of this with the rational points of the curve is finite. And we have Falting Theorem. Nice. Well, nice. I mean, 5 lines proof, 6 lines proof. Okay, not, no, well, there are more lines on the other side, but okay, not such a big proof, but actually it's because we are assuming here Botja inequality. And actually it is Botja inequality what is very difficult to prove. So, I mean, in the references that I gave you, that you can look at them in my notes, you have some links. There is a proof, or well, no, it's not a proof, but you have the ideas of the proof of Botja inequality, just in case you want to look at it. And the other funny thing that you can find in my notes, I told you that, okay, so we proved that the set of rational points is finite, but there is this question about, okay, but now how can I compute this set, this finite set? And I mean, there are a lot of strategies and a lot of people that have worked on it. And I mean, I put you in my notes like 2 links to surveys of people explaining which ones are like the best strategies depending on the cases and everything. So, I mean, I really invite you to take a look if you are curious about it. Okay, so this was about Falting theorems. So now is the moment to move to open problems, okay? So I'm going to tell you something about open problems. So, of course, I mean open problems on Diophantine geometry. So, I mean, if we think about open problems in Diophantine geometry, there is one that is the most important one. Well, I don't know if important, you will see, because actually, like, it implies like all the other results that you can imagine in Diophantine geometry. So, I mean, in this sense, it's very important, but actually, it is also like very famous right now. You will see why. As soon as I say the name, you are going to say, oh, yes, I know. So, I mean, I'm going to state it as an open problem. The polemic is coming. So, conjecture, ABC. So, the ABC conjecture, that even is a little bit polemic that I'm saying conjecture, because there is a person that claimed having a proof of this theorem. You know, this was a Japanese mathematician that in 2012, Mochizumi, he claimed that he proved the ABC conjecture. We are going to discuss all the implications about the ABC conjecture. This is huge. This would have been huge if we really had a proof. The problem is that the proof was very, very complicated, very, very, very long. Like some of the best mathematicians, alive mathematicians, tried to understand this proof, and they didn't manage. And even they think that they found a gap in the proof. So there is a step in the proof that is not clear. They think that it's not true. And Mochizuki claimed that he could fix it, but so far it's not fixed. So far we don't have a proof. And it's a pity because, I mean, this is a very strong result. You will see. So, I mean, let me state it. So the ABC conjecture was claimed to be true by Maser Oesterle. And it says that for all epsilon greater than 0, there exists a constant that depends on epsilon, so I call it C sub epsilon, such that if A, B, C are integers, coprime, and satisfying that A plus B plus C is equal to 0. So, I mean, this is why this is called the ABC conjecture. Then, and here are the heights coming up, the maximum of the absolute value of these 3 integers is less or equal than the constant times the radical of ABC to the power 1 plus epsilon. Who is the radical, just in case you don't know it? So the radical of an integer is equal to the product of all the primes that divide the integer. But then you remove the exponent. So if p squared divides n, you only consider p1. So this is the ABC conjecture. So how should you understand it? So actually you should understand it as saying, so basically the radical is almost equal, so it's smaller than the product, and it is almost the same thing when you have like small powers of the primes dividing this. So basically this is saying that because this is smaller or equal than this up to a constant, it means that the radical is relatively big. So it means that when you have something like this, it may not happen that you have big powers of a prime dividing the numbers here. So this is the intuition, if you want, more or less. Okay, so here we have the conjecture. And why I say that this conjecture is very important, because actually this conjecture implies, if it is true, this conjecture implies load of famous conjectures. So for instance, it implies Fermat-Last theorem. It implies Falkens theorem. So, okay, let me say something. Falkens theorem is already proved, so we just saw a proof based on Bottia inequality. But we would have like a trivial proof if this would be true. Fermat-Last theorem, well, at least an asymptotic version. So, I mean, you know that Fermat-Last theorem is a theorem. It is proved by Wiles in the 95. So 25 years ago, 26 years ago now. But I mean, the proof of Fermat-Last theorem, I always say it, I mean, I really think that is one of the most difficult proofs in mathematics. So, I mean, this is not at all a trivial result. And the ABC conjecture implies Fermat-Last theorem. So, I mean, this is really huge. Like, I mean, this conjecture is very strong. I mean, if it is true, and yeah, I mean, we all believe that it's true. But if it is true, it is really strong. It implies a lot of results. So, I mean, it would imply these two theorems, but then it would imply too, and I mean, I'm not going to state the, you may find the statement of these conjectures. So this is a conjecture, this is not proof. This is another conjecture, it's not proof. And this is a conjecture, it is not proof. So Spiro, Frey, and Land conjectures, that they are also open problems in the Diophantine geometry. If you are curious about it, go to my notes and you have the statement of those conjectures. But all of them, they are also implied by the ABC conjecture. And even I can also give you another theorem on Diophantine geometry, that is Roth theorem. So, I mean, this is in approximation geometry. It is like a very strong result again. So, I mean, this is also proved by Roth. But again, it's like a very strong result. And it is implied by the ABC conjecture. So, yeah, I mean, wow, imagine proving it. Okay, so what are we going to do? So, I mean, I could state those results that you don't know, the last four, but those ones, I mean, you just can look at them at the notes. So what I'm going to do, and I think that is funny, is to see how the ABC conjecture implies Falkens theorem. So we are going to see a different proof of I mean, it's not a different proof because we don't know if this is true, that is not a proof. But if it were true, then we would have another proof of Falkens theorem. So we are going to look at this proof, okay? So let's see how we do this. Okay, so proof ABC implies Falkens theorem. Actually, the proof that I'm following is by Elkis. He's a very good mathematician with very nice results. And I mean, he came up with this proof of Falkens Theorem by using the ABC conjecture. Okay, so the idea is the following. So, for any rational number x different from 0 and 1, I need to introduce some notation, n0 of x equal to the product of the primes such that the order of x at p is greater than 0. So this is like the radical, right? I mean, this is just the radical, but I need to call it in this with this notation. You will see. N1 of x, I define it as the product of the primes such that the order at p of x minus 1 is greater than 0. And then I define n infinity as of x as the product of the primes such that the order at p of x is negative. Okay? So by inducing this, and now I set n of x equal to the product of these three things, we can restate the ABC conjecture as follows. So we can write it as this is greater or equal than this. Okay, so now let's take, because so far we haven't seen any geometry, and Falkens theorem is about geometry, so let's take our curve. Let's see. So I'm doing the proof over the rationals. Falkens theorem is over number fields, but I mean, we can just do it over the rationals, and the proof is very similar over any number field. Be a curve of genus greater or equal than 2. Then, Bailey's theorem. So, I mean, this is a theorem in geometry that we haven't seen, but I'm telling you what it is saying. So, Bailey's theorem says that there is a finite map from the curve. So, I'm going to call the map F. Okay? From the curve to P1, say of degree D. So we don't know anything about D, but it is finite. That is ramified only above the points 0, 0, 1, and infinity. Okay? So this is Bailey's theorem who tells us that we can find such a morphism from the curve. Okay? So let me call M equal to the number of preimage of 0, 1, and infinity by these maps. Okay? So now I can use Riemann-Hurwitz theorem to this map, to this morphism. So if you don't know Riemann-Hurwitz theorem, don't worry, just take it as is giving to you what I'm saying. If you know what it says, good, because then you know how to deduce it. That 2 times g minus 2 is equal to minus 2d plus 3d minus m. This is coming because the degree of the morphism is d and the genus of the P1 is 0, and this is a contribution that is coming from the ramification points of the morphism. So we have this, but this we can develop it to get this thing. Okay? So now I'm going to get epsilon smaller or equal than 2g divided by 2 minus 2 divided by d. Okay? So any epsilon satisfying this thing. Why do I want this? Because if I have this, then m divided by d is smaller than 1 minus epsilon. That is the terms that appear here. So I'm just rewriting things in a different fashion. So now I need to take some divisors. So let t0 equal to this divisor. So basically the zeros associated to f. So maybe I can just write it. Yeah, well, let me add the zeros, okay? So the points at which the order of f at those points is greater than 0. So the zeros. And then I get another divisor, d0 prime, that is kind of the same divisor, but I'm making all the integers here equal to 1. So I'm just only taking the points. So I take this equal to the sum where the order of q of f is greater than 0 of q. So I take these two divisors and I call the degrees, the degree of d0 equal to d0 and the degree of d0 prime equal to a small d0 prime. Okay? This is a little bit of notation. So I continue. So we are going to have a proof, but I mean, we need some work to get the proof. Okay, so with those divisors that we have just defined, we have that the divisor d prime 0 d0 minus d prime 0 has degree 0. Okay? So it is algebraically equivalent to 0 in C. And moreover, d0, because of the way that we define it, is ample. So we can use the Veil height machinery to have that the height associated to this divisor d prime 0 is equal to this. Of course, up to a constant. So if I remember correctly, now I'm not sure, but I think that this is lecture 2 that we proved those results. Okay, so we have this equality. Now, let P be a rational point on the curve with f of P not a 0 or not a pole. So this is okay, right? Because the number of poles are 0 is a finite number. So we can forget about these numbers. We just have to check that the points such that f of P is different from 0 and infinity, there is also a finite number. Okay, so a prime occurs in the numerator of f of P if and only if it contributes to the height, the multiplicative one of the point, right? because recall that, I mean, this height, we do the product that runs through all the valuations, and we take the maximum of those valuations. So in order to contribute to this height, we need the prime p to appear in the numerator. Okay, so this implies that what we call N0 of Fp is smaller or equal than this thing, right? Because this is only a part of the things that appear here. So now we can take a logarithm of this, and then we get that the logarithm of this is less or equal than the logarithm of this. But if I take the logarithm of this, I get the logarithmic height that appears here, and that is equal to this up to a constant. So this is smaller or equal than d prime 0 divided d, the height, plus a constant. So I'm going to be clear, this constant, so we are not cheating, depends on this, right? Because depends on that. And now we can rewrite this as follows. So the first term is the same thing. And this, we can rewrite it in terms of the height of the point, right? Okay, we are almost there. So, I mean, we did this argument with the 0, with n0. But actually, we could have done exactly the same with n1 and with n infinity, just changing the 0 by 1 and infinity. And then we can use, the d is going to be always the same. So, I mean, we have this inequality, so that the logarithmic of this thing is less or equal than this thing, okay? So here we're going to consider 0, 1 and the point at infinity. Here we get the same constants, here we get the same thing, This is the only thing that changed, okay? But now recall that we had that m was equal to this thing. Right? So if I use this, then we get that the logarithm of n of fp is less or equal than this. So we get this, but now the ABC conjecture tells us that for any epsilon, so sorry, I need to, yeah, this is a very long proof, sorry guys, but we are almost done. We are 2 lines to the end. Okay, so we have gotten this inequality, okay, this last one. But now what is the ABC conjecture telling us? So it's saying that for every epsilon greater than 0, there exists a constant that depends on epsilon such that the logarithm of n of fp is greater or equal than this. Another parenthesis, right? With the reformulation that we saw just before. So then this implies that 1 minus epsilon minus this of this is less or equal than another constant that depends on epsilon, but only on epsilon. And remember that now if we take the epsilon as before, that it was smaller than 2g minus 2 divided d, it was in order to get that this thing is positive, right? So that this number is very small. This we can do it. So if this is very small, then this is still positive, and that's what we got. Then what we got is that the height of the image of the point is bounded. But then in particular, the height of the point is bounded. And then there is only a finite number of points with a bounded height. And then we are done. We get a finite number of points. So, I mean, I don't know, you want me, okay, so I'm going to write it. And we get an upper bound for the height of P. So, the number of rational points is finite. So, okay, second proof of Falkens theorem. And I mean, actually there is something very nice too, and it is that imagine that we have a proof of the ABC conjecture, and even imagine that we have an explicit proof. So that we have a proof in which we were able to compute the constant C epsilon. Then, in this case, we also have a explicit constant for the height of the rational points on the curve. So we would have an effective Falkens theorem, proof of the Falkens theorem. So that could be great and amazing, but well, unfortunately, we still don't have it. So maybe if you like it, you can keep doing research on this, and maybe one day you can find a proof. Okay, so with this, I'm done for today with this lecture and with this course. I really hope you enjoyed, and yeah, please email me, ask questions, take the opportunity. If there is something that is not clear, ask me, so I can re-explain and I can give you more references if needed. And that's all. Thank you very much, and hope to see you in person. I don't know when. Bye.